Alrighty then. A little bit of a different video today. This is something I did back as a joke in the Ghost Recon Wildlands days, where I calculated maximum range of a bullet in Wildlands, just as something fun to do. And if you're anything like my friends, you would say I have a weird idea of what fun is, and you would be right. Many fans of the Ghost Recon series are probably familiar with Dark Daily and his legendary 3-kilometer shot, where he held an enemy while his friend shot at them from a mountaintop about 3 kilometers away. But screw that, how far can we really shoot? First things first, what am I actually calculating? What does maximum range mean? There's a couple of ways to approach the question, and for this video I'll be taking a standardized approach, and I'll explain why in a second. For this video, we'll be measuring the theoretical distance from the shooter a bullet would land if you shot at a perfect 45-degree angle to the horizontal. The reason for this interpretation is because you can manipulate the question a million different ways by changing basic variables. If you change the height of the location of the shooter, the bullet will go farther. If you decrease the elevation of the location where the bullet lands, the bullet will go farther. If you change the elevation of the shooter to be higher and the bullet hit location to be lower, the bullet will go even farther. I cross off doing it this way for a few reasons. The first of which, as mentioned, is that you can always change it by adding another meter of elevation. If you want the longest possible shot, you could get a friend in a helicopter, fly to the height limit, shoot off the side of the heli at a 45-degree angle, and that would be the longest possible shot. However, doing so would never be practical, as I'm pretty sure the bullet would unrender before it hit the ground. So for this test, we'll be measuring distance on theoretical flat ground. We can measure the length of the path of the bullet, but A, why would you ever need to know that? And B, doing so would require me to get into calculus to do an approximation of arc length with Riemann sums, and I really don't want to do the calculus for this. It's a lot of unnecessary hassle for a relatively pointless statistic. Basic algebraic physics should be sufficient for this equation. For the video, I'll be using the TAC-50 sniper rifle, as it has the least bullet drop in the game, as far as I think, meaning it should have the most distance. We also want anything that can increase our maximum range. I'll be using the Ballistic Advantage perk, which gives plus 60 range, the bipod, which gives plus 10 range, and the sniper roll itself has plus 20 range, for a grand total of plus 90 range on top of the TAC-50's already enormous range stat. Let's go over assumptions for this. Assume we are on flat ground that goes out for miles. Wind resistance is negligible, because I doubt Ubi, just import the old assets soft, would take the time to code in wind resistance for a video game with already unrealistic physics, and we're going to prove this later. And we will not be using any abilities that affect bullet drop, like the Marksman's class special ability. I'll say why later. Now it's time for data collection. In order to figure out maximum range, we need to know two things: bullet velocity and how much the bullet is affected by gravity. First one is easy. Start up a mission that allows me to hit long-range targets, and I could count the frames between firing and getting a hit marker to determine velocity. Easy. Finding out how much each bullet is affected by gravity is a bit harder. The problem with having a rifle with so much range is that bullet drop before 500 meters is negligible. You can aim at someone's forehead 500 meters away and it'll hit them in the chin. On top of that, bullets get very hard to see past 400 meters. You can't exactly see where the bullet hit someone. You just know you hit them because they get really tired and they take a long nap as soon as you hit them. So we need to find some range, longer than 500 meters, where we can see where a bullet impacts. Problem is, there's very few 600 meter sight lines anywhere, much less flat ones. After searching for a few minutes, I found a beach that was relatively flat. Not perfect, but it's my first idea. Okay, so we have testing range. Now we need something to compare it to. Notice a truck, Starfield X4, sitting on the beach near some hostiles. Took them out and went for a joyride in a new test range truck. Now I needed to know how tall the truck was so I could tell how far the bullet fell. Again, easier said than done. My first thought was to go on the wiki, figure out which real-life truck it was based on, and then find the height of its real-life counterpart so I could determine how far the bullet fell when I aimed at the top. Well, another problem. The beach, while relatively flat, was not at all flat. I needed something like ex-girlfriend flat. I could tell the beach wasn't flat because when the character releases their drone is released at roughly head level, and the drone would skim the ground if it moved in a straight line without changing elevation. So I already had to aim at an angle to hit the truck, which would throw off my measurement. Other than that, I couldn't find any data on how tall the truck was anyway, so even if the beach was level, I'd have no idea how far the bullet fell. So I blew up the truck and started looking for a different idea. That's when I noticed the water. Water, taking the shape of its container, will always have a flat surface on an open top. It's still not ex-girlfriend flat, but it'll do. I figured I could aim above the water and figure out how long it took to splash on the water surface. In case you never watched Mythbusters as a kid, a bullet fired from the gun and a bullet dropped from the same height will hit the ground at the same time. There were quickly two problems with this. The first one is that I had no idea how high above the water I had to aim in order to ensure I was aiming at a parallel to the water surface, as any angle change would dramatically affect my gravity calculations. The second was that shooting over the water surface causes the bullet to take a page out of the book of Schrodinger, and both collide with the water and not collide with the water at the same time. Now, already I could tell this method wasn't going to work, so it was time to look for a new one. Just as I was about to give up, I noticed what looked like a small outpost off the coast of the opposite bank. This outpost had a small white box on the dock, probably an electrical box. So I pulled out my drone and flew toward the box without changing the elevation of the drone. And remember when I said the character releases the drone at head level? Top of the white box is perfectly at drone level and thus head level. On top of that, my character was standing at exactly water level, so I could tell exactly how tall the box was. I also confirmed this by standing next to the box and moving the camera to an angle where I could compare its height to the character's height. Turns out, they're pretty close to exactly the same height. Okay, now I had something to measure against. I went on the wiki and searched for the character, Nomad, and how tall he was. After finding nothing on the wiki, I turned to the internet's #1 source for factual and correct information. I went to Reddit. I found one comment saying Nomad is 6'0", and after looking at his character background, I decided that was a reasonable estimation and figured it was my best shot at figuring this out. After confirming my discovery, I now had an accurate scale for bullet drop. Our first test is for the bullet velocity. For accuracy, I did this test multiple times at multiple ranges. First test was on a target 400 meters away. Started my frame count at the frame just before you could see the bullet on screen, and stopped the count on the first frame where the hit marker was visible. Here's that clip. From the frame before the bullet to the first frame showing the hit marker at 400 meters was a total of 16 frames. This means the bullet traveled exactly 100 meters in 4 frames. If I was previously right that Ubisoft didn't code wind resistance into Breakpoint, then we should be able to figure out how many frames each shot should take in each interval of 100 meters. For a 500 meter shot, using the same system, it should take 20 frames. Well, here's that next shot. As expected, it took exactly 20 frames at 500 meters, proving that once in air, bullet velocity does not change and wind resistance is negligible. Testing this on farther ranges is much harder because enemy markers stop rendering around 530 meters, but for what we have, this will be good enough to draw conclusions from. Next part is the hardest part, figuring out gravity. That's where this white electrical box comes in. I found a spot on the beach that was exactly 650 meters away and started blasting.
Anyway, I started blasting.
When I say I took a ton of shots, I mean I took a good 200 to 300 shots at this box. With the slight movement of the waves, reticle sway, and the general inaccuracy at that range, taking one shot and using that as a baseline was not good enough. I figured that, through the law of large numbers, eventually I would see layer clusters on the box where most shots were hitting. That would be what I used for the gravity calculation. Here's a couple screenshots showing my bullet distribution over time. Keep in mind, these were all at 650 meters. They might not look like much, but one screenshot in particular stood out to me. I had a perfect cluster of shots all around one elevation. This would be the screenshot I could use to calculate the drop. In order to calculate for gravity, we need to know how far the bullet fell and how long it took to fall that far. Using our previous velocity calculation, 650 meters, the bullet would have taken 26 frames to hit. In 60 frames per second, each frame is 0.0166 seconds. 0.0166 seconds per frame times 26 frames equals 0.433 seconds. Opening up Photoshop, I made a standard 1920 by 1080 file and imported that previous screenshot. Took a guess as to the rough middle of those shots and decided to use that as my baseline. Measure the height of the box to be 367 pixels, and the distance from the top of the box to the average hit location to be 276 pixels. Since we said the player is 72 inches tall, 6 feet, and the box is the same height as the player, the box is also 72 inches tall. Now, as much as I love the US Imperial measuring system, when it comes to physics, Imperial doesn't cut it. Metric's the way to go. 72 inches is 1.83 meters. Divided by 367 pixels, that means each pixel is 0.004986 meters. We can do the same thing with our bullet drop. 0.004986 meters per pixel times 276 pixels is 1.3761 meters. As previously established, this whole flight took 0.433 seconds. We need to know acceleration due to gravity, so we can plug all of this into the equation d equals v sub I t plus 1 over 2 at squared, where d is distance the bullet fell, v sub I is an initial velocity, and t is time. Bullet starts at rest, so v sub I is 0. Since anything multiplied by 0 is 0, this first part of the equation can be removed entirely. D resolves to 1.3761, t squared resolves to 0.18777, or 0.433 squared, and now we can do some simple algebra and solve for A. All this comes out to a gravitational acceleration, 14.6573 meters per second squared. Now, all that's left to do is calculate the final distance. There's a couple ways to do this, but we're going to do it the simple way with the equation sine 2 theta times v squared divided by g. Theta is our angle of launch in degrees, or 45. V is initial velocity in meters per second, and previously established, bullet velocity is 4 frames per 100 meters, or 25 meters per frame. Since there are 60 frames in a second, we do 25 times 60 to get 1500 meters per second. And now we can solve. Sine 2 theta resolves to 1, 1500 squared resolves to 2.25 million, and g is 14.6573. Divide it out and we get, drumroll please, oh wait, I'm the editor, I gotta add that in. Try it again. Drumroll please. 153,507.126 meters. Divide by 1,000, and we get 153.5 kilometers. Now, if you're like me, you saw that number and said, there's no way. I can barely hit shots at 700 meters. How is it going to go 153,000 meters? Well, I ran the numbers using a different equation for solving for flight time and multiplying the horizontal velocity component by that time, and got the exact same answer. So I know my math isn't wrong. Remember back when I said I think the bullets take a page out of Schrodinger's where they both hit the water and don't hit the water at the same time? I think the same thing is happening again. I think the bullet you can see and the bullet that hits the target are two different objects. When I was doing testing for this, sometimes I would shoot low and see sparks emit from the bottom of the dock. I looked at the frame count and it was exactly 26 frames, or when the bullet should have been hitting, but the spark shot out, we could still see a bullet tracer in the air. Now, I don't work for a Ubi, just import the old assets soft, but I have spent a couple years trying to design my own FPS game, and one of the things I learned is that if you have projectiles moving too fast, they can clip through targets, even if they're a direct hit. That's why games like Rainbow use raycasting and hit scans, even though it's very inconsistent at times. Yes, Rainbow fans, please don't sue me. If I had to guess what's happening, it's that the bullet tracer waits to see if the actual bullet raycast hits a person or robot, and if it does, despawn the tracer. If it doesn't hit a person or robot, do nothing. This would explain why we can see both the tracer and the impact at long ranges. So one last thing before we close out. The reason I didn't use the marksman ability was because of how long it would take to get an accurate reading. Get 5 shots, now go kill a bunch of enemies, find the exact same spot again. It was just too much of a pain. From the shots I did test, I wasn't getting much different results. Of the 15 shots I fired, about 10 of them fell pretty close to where the other estimated middle was. It wasn't statistically significant enough that it would do much of a difference. So, now we know. If you stood in flat ground and shot a perfect 45-degree angle, your shot would go just over 153.5 kilometers. If you liked the video, please consider liking and subscribing. And like a lot of YouTubers, I will never do that thing where I say blank % of viewers aren't subbed, but I will ask you to consider it. I mainly do funny gaming moments with my friends, and it's always a fun time, so if that sort of thing interests you, hit the big red button. It costs absolutely nothing, and you get free entertainment. It's a win-win.